So why are you guys getting all uppity with us? Right? And then Rod Johnson comes along and says, yeah, we can take POJOs, right? Forget objects. Objects are old names. Let's call them POJOs. Right? Plain old Java objects. And I'll put my own brand of container around it. And now instead of implementing interfaces, just put a name there, right? And I'll just sort of poke into your object and give you stuff, and we'll call it dependency injection. We'll give it a snazzy new name. We'll call it inversion of control, right? We'll sort of allude to famous movie stars from Hollywood, and we'll say, don't call us, we'll call you. You had no choice. You had to love it. It was engineered that way. But guys, here's another secret shame. Spring is not intrinsically object-oriented either. It's an attempt to create a transaction-oriented system, but again, transaction-oriented systems are not intrinsically object-oriented. And we'd sort of limped in this mindset for quite a while until one day, a guy working at the University of British Columbia decided he was going to create a new language. He'd had some experiments with Common Lisp, the Common Lisp Object System, CLOS, where pretty much everything is fair game. You can do whatever you want, right? You can add methods, remove methods. You can do all kinds of crazy stuff in CLOS. And he said, you know what? I realized that people doing that created write-only code. You guys are familiar with write-only code, right? Goes by another name, Perl. Code you write once and can never figure out how it works again. Come on. Somebody in here has written some Perl before, right? Right? Thing of it is, he realized people were getting themselves into trouble because the language didn't restrict things enough. So what he wanted to do is he wanted to create a constrained subset of this kind of meta-object programming. And so he built a language, and then he said, what exactly do I want this thing to emit? Well, I know, I'll have it emit code onto the Java bytecode format. And he called his new style of programming aspect-oriented programming. And of course, the language was AspectJ, and the gentleman's name was Gregor Kozales. And AOP emerged onto the world, and it was like a wake-up call. All these Java developers who had sort of snoozed their way, once you got done with object-oriented programming and learning about, is-a style inheritance and has-a and all those other kinds of verbs, right, in terms of how do we do object design and so forth, they'd slept ever since then because this was how people wrote things. We built POJOs, we built transaction things. All of a sudden it was bing, wake-up call. And they said, wow, this is, what do I use this for? Well, you could use aspect-oriented programming for tracing. We can capture all of these concerns, as they called them, and capture them up in a single first-class concept, just like we did with objects 20 years ago. Capture up all of the state and behavior that builds around objects into a first-class concept. And we went, whoa, that's cool. And we played with aspects, and whether or not aspects were successful or not, they did something very, very important. It made us realize that God doesn't think in objects. Turns out that God thinks in Ruby. No, I'm teasing. What it means is that we still don't know how God thinks. That there are other ways to look at how we want to break a problem down and turn it into some sort of executable code. The functional language community has a very, very different approach to how they build software. They think about software in terms like mathematical functions. You have inputs and they produce outputs, and there's no shared mutable state, which means then it makes it very easy to scale things up. Makes it very easy to scale things out because we just throw more data at these functions. There's no shared state whatsoever. This is known as a pure functional language. Paul Graham, who talks a lot about Lisp, says that all the great ideas in languages have come from Lisp. Yeah, okay, whatever. But it turns out that a lot of really interesting ideas they showed up in Lisp first. And his contention is that every so often, programmers get kind of tired of the language they work with, so they'll go off, they'll grab a new idea from Lisp, they'll bake it into their language, they'll claim to have invented it, and then, we'll sit on that for another 10 years. Graham's assertion, of course, is that once you know Lisp, well, this is what God thinks in, so you're done. Now, I don't know that I agree with that, but the fact is that there are definitely some very interesting ideas inside of Lisp that we have definitely incorporated into our languages, right? Conditionals. How many of you could imagine programming without if? Or recursion, the ability to call the same function, or garbage collection. Within our lifetimes, we've seen the transition from garbage collection is what you do when you're a bad programmer to garbage collection is what only bad programmers would avoid, right? I mean, think about it. How many of you really want to go back to doing your own memory management? Yeah, my point exactly. And it's a good thing that we're working on, we're thinking about these ideas around these different languages because the challenges that are coming up to face us are pretty huge. The concurrency issue is by far and away the most obvious. If you go purchase a machine today, right, the fastest processor that you can pick up is like what, 2.5 gigahertz? And if you were buying a machine 4.5 years ago, the fastest processor you could get was what, 2.5 gigahertz? 3 gigahertz, maybe something like that. What happened? Did Moore's law just give up? You guys remember Moore's law, right? Moore's law is the one that says that the number of transistors we can put on a piece of silicon doubles every 18 months. And that turned into, for us as developers, that turned into the Quake rule. You guys know what the Quake rule is, right? No? Well, maybe this is a states-only thing. See, when your boss comes to you and says, hey, the application is running too slowly, you say, let me do a little analysis here, boss, and see what I can come up with. And you go back to him in about a week and say, after careful analysis of our code, I think we can achieve a 2x performance improvement. Really? 2x? 2 times faster than it is now? That's amazing. I was thinking maybe we'd get 5 or 10% faster, but 2 times? Wow. Well, what are you going to have to do? Well, I'll tell you what, we're going to work on it for 18 months. And in the meantime, you play Quake. 4.5 years ago, a 3 gigahertz processor was the top of the line. That's 3 Mooresian cycles ago. What happened? Intel ran into a very, very fundamental problem. You may have heard of it. It's called the speed of light. Anybody heard of that one? Yeah. This guy down here is like, I'm going to raise my hand again. You really shouldn't do that. You will never forget this keynote, ever. It turns out that Intel discovered that they cannot get a signal from one end of the chip to the other in a single clock cycle. That was the limitation they ran into. And so they said, okay, let's see. If we don't make our chips faster, we won't sell any more chips. So what do? How about we take the current chip we've got, carve it in half, and call it a Core Duo. And it worked. People bought them. Because if one chip is good, 2 chips must be better. And if 2 chips is better, 4 must be even better than that. God forbid when we get to 8 or 16, we're going to be like, oh my God, this is orgasmic. But think about this for a second. How many of you, we'll go back to this question earlier, how many of you write perfectly thread-safe code? He's back over here somewhere, right? Yeah, there you are. He's the only one who gets to use the Core Duo. The rest of you are going to have to use just one of those cores because if your code's not thread-safe and you're running on, multiple CPUs, your users, well, let's just call the spade a spade. Your users are fucked, right? Because if you can't guarantee that your code will thread safely on a single CPU, God help you when you get to multiple CPUs, and your code's not going to get any faster. This concurrency problem is huge. Absolutely huge. This is the dragon we must slay in the coming decade. And what's the solution? There isn't one yet. We're still working on it. Guys at Microsoft, guys at Sun, guys at Oracle are desperately burning the midnight oil to find a solution because, the solution right now is synchronized.